4 completely different systems that regulate life on this planet have all started behaving strangely at almost the same time. The ocean current that keeps Europe from freezing is wobbling. The jet stream that steers our weather is fragmenting. The polar vortex over Antarctica just did something it has never done before in 44 years of satellite records. And Earth's own magnetic North Pole is moving in a way nobody predicted, then suddenly slowing down in a way nobody predicted either. 4 systems, 4 sets of scientists, and 4 papers that all land on some version of the same uneasy sentence. We don't fully understand why. Sea surface temperature anomalies keep showing up in the North Atlantic in Patayane's older models didn't predict. Meteorologists keep describing jet stream behavior as unprecedented in press briefings that used to reserve that word for once-a-decade events. NASA researchers watched Antarctica do something in 2024 that has never once been recorded in 44 years of continuous satellite monitoring. And geophysicists tracking the magnetic North Pole have had to issue emergency updates to navigation models because reality moved faster than their forecasts. So is this a coincidence? Is it one underlying cause? Or is it something else entirely? Several unrelated stories that just happen to be making headlines in the same stretch of years. Let's go through the actual science behind each one item at a time, because the honest answer is stranger and more interesting than any single scary headline. Every few months, a headline claims the Gulf Stream is collapsing and Europe is about to freeze. Almost none of those headlines are describing the Gulf Stream correctly, and that mistake matters more than people realize. Start with where all ocean and atmospheric motion comes from. The sun. Solar radiation heats the planet unevenly, warming the tropics far more intensely than the poles. That warm air rises near the equator, cools as it moves through the atmosphere, and eventually sinks again, forming giant loops of atmospheric circulation. Earth's rotation acts on those loops and bends them into what we call prevailing winds, the real engine behind surface ocean currents. In the North Atlantic specifically, those winds are the northeast trade winds that carried Columbus toward the Americas, and the westerlies that carried ships back the other way. Those same westerlies are part of the reason a flight from New York to London is shorter than the return flight. Wind-driven surface currents get pushed into a rotating elliptical loop between the continents bordering the Atlantic, and Earth's rotation strengthens the current running along the western edge of that loop. That strengthened current is the Gulf Stream, roughly 50 to 150 kilometers wide, several hundred meters deep, and one of the most powerful currents on the planet. Here's the detail that trips up almost everyone, including plenty of journalists. Look at satellite infrared imagery, and the Gulf Stream is not off the coast of Europe. It runs up the eastern coast of the United States and Canada. It never reaches Europe at all. So why does everyone say the Gulf Stream keeps Britain and Norway habitable? Because the current that actually reaches Europe is a different one, the North Atlantic current. The Gulf Stream flows northeast along the American coastline, merges with other Atlantic currents, and becomes the North Atlantic current somewhere out in the open ocean. That distinction matters enormously because it means that even in a scenario where the Gulf Stream itself weakened, that wouldn't automatically mean the North Atlantic current collapses too. The Gulf Stream is one contributor to it, alongside other warm water sources like the Canary Current running down the west coast of Africa. So when people say the Gulf Stream is shutting down, what they almost always actually mean, whether they realize it or not, is something bigger. The Atlantic Meridional Overturning Circulation, or AMOC. The Gulf Stream and the North Atlantic Current are both pieces of this larger system, which carries warm water from the tropics up into the North Atlantic and sends cold, salty water back down toward the Southern Ocean at depth. Along with equivalent systems elsewhere, like its counterpart in the Pacific, AMOC plays a huge role in regulating global climate, distributing heat and salt around the planet, and influencing the carbon cycle. Here's the genuinely important distinction. The Gulf Stream is driven mainly by Earth's rotation acting on wind patterns. AMOC is driven by something completely different, thermohaline circulation. Warm, relatively fresh water travels north from the equator, cools as it approaches pole, and because of its salt content becoming more intense, becomes dense enough to sink. That sinking pushes cold, salty water into the deep ocean, where pressure and density push it back toward the equator at depth. Along the way, it warms again, rises back to the surface near the tropics, and the cycle restarts. This is the process that climate change can genuinely affect. Arctic ice is fresh water. As more of it melts, it dilutes the salt content of the surface ocean in the North Atlantic. Fresher water is less dense, and less dense water doesn't sink as readily. If enough fresh water pours in, it can slow or even stall the sinking that keeps the entire AMOC cycle turning. Whether and when that could actually happen is a genuinely contested question among climate scientists, and anyone giving you a confident, specific date is stretching well past what the current evidence supports. What we can say with confidence, the Gulf Stream itself is not going to stop because of climate change, because nothing about a warming planet is going to stop the Earth from spinning. If climate change disrupts anything here, it's AMOC. And even that remains genuinely unresolved, since these massive circulation systems respond to many factors, not all of them human-caused. An AMOC slowdown would shift the Gulf Stream's path somewhat, pushing it further south, but it would not simply switch the Gulf Stream off. And here's a genuinely counterintuitive twist. Some climate researchers, including physicist Tim Palmer, have argued that a slower AMOC might actually push the Gulf Stream's path further south and cool northern Europe's regional temperatures, potentially offsetting some warm G in that specific region, and possibly even helping stabilize Greenland's ice sheet in the process. For people living in Europe, that's a mixed blessing at best. A cooler regional climate isn't automatically comfortable news either. And even in the most severe modeled scenarios, once AMOC stalls, it could take thousands of years to restart. We also know from the geological record that AMOC has collapsed and restarted multiple times throughout Earth's history through entirely natural cycles long before humans existed. So some version of this shift is not something we can prevent forever, regardless of what we do about emissions. It's also worth understanding why this topic generates so much disagreement among scientists in the first place. AMOC is monitored today mainly through an observation network called RAPID, which has only been continuously measuring the strength of the overturning circulation across the Atlantic since 2004. 2 decades of direct measurement is a genuinely short window to judge a system that operates on timescales of centuries, which is exactly why researchers reconstruct older AMOC behavior indirectly, using proxies like deep-sea sediment, cores and temperature records preserved in ocean floor deposits. Different proxy methods sometimes disagree with each other, and that's a meaningful part of why headlines about AMOC collapsing by 2025 or 2050 tend to outrun what the underlying data can actually support. The NEST scientific consensus is that AMOC has very likely weakened somewhat since the mid-20th century, that further weakening this century is a realistic risk worth taking seriously, and that pinpointing an exact collapse date is currently beyond what the evidence allows. From the ocean, let's move to the sky, where something dramatic has been happening to the jet stream, the band of wind that steers much of the planet's weather. A jet stream is a fast, narrow river of air that circles the globe in large, wave-like bands. It forms because of temperature and pressure differences between the tropics and the poles. Air near the equator is heated far more intensely by the sun than air near the poles, and that temperature gap creates zones of high and low pressure. Air always moves from high pressure toward L-line. High pressure, generating horizontal currents, and Earth's rotation deflects those currents east and west through the Coriolis effect. That deflection is what forms the jet stream. There are 2 main branches, the polar jet stream at higher latitudes and the subtropical jet stream closer to the equator. Recently, meteorologists have described the jet stream, particularly its behavior over North America, as unusually fragmented and unstable. Instead of flowing in a smooth west-to-east ribbon, it's been breaking into pronounced, wavy, erratic patterns. That instability has been king heat waves in multiple regions, with reported temperatures in parts of Mexico climbing close to 50 degrees Celsius during peak events. So what's actually causing this? Climate change is genuinely one contributing factor. As regions farther from the equator warm faster than the tropics themselves, the temperature contrast between the equator and the poles shrinks. Less contrast means weaker pressure differences, which means a weaker, more erratic jet stream overall. But it would be misleading to pin this entirely on climate change, because there's a much more immediate, well-understood factor at play too: El Niño. El Niño is a natural climate pattern defined by warming surface temperatures in the equatorial Pacific. Even though it starts as a regional event, it has genuinely global effects because it reshapes both ocean and wind patterns. During an El Niño event, the usual temperature contrast between the eastern and western Pacific narrows, altering pressure patterns in ways that directly disturb the jet stream, contributing to instability and fragmentation. Jet stream bands get disrupted and deflected at higher latitudes, which can lock high pressure systems in place over certain regions, producing prolong. Jet heat waves, or in some cases unusual cold snaps, while low-pressure systems stall elsewhere and dump heavy rainfall or trigger flooding. This same mechanism partly explains why El Niño boosts hurricane activity in some parts of the world, while suppressing it in others. According to America's National Oceanic and Atmospheric Administration, as the zone of warmest water along the equatorial Pacific shifts, the region of greatest evaporation into the atmosphere shifts with it. And that has a significant effect on the jet stream's average position. Given that meteorologists identified the recent onset of a new El Niño phase following a pre-Ding La Niña period, the timing lines up closely with the jet stream disruptions we've seen. That timing strongly suggests El Niño is the primary driver here, with climate change likely amplifying the effect on top of it rather than being the sole cause on its own. Now let's talk about the polar vortex, sometimes described, fittingly, as an icy guardian, normally locked behind an invisible wall. That wall is the polar night jet, a fast-moving band of wind circling the Arctic that separates the polar vortex, a massive pool of extremely cold, low-pressure air, from the rest of the planet. As long as that wall holds, the coldest air on Earth stays contained near the pole instead of spilling south. Sometimes, though, the wall doesn't hold. When the polar night jet weakens, or even splits into two separate branches, cold air from the vortex can suddenly spill southward into much lower latitudes. This is called a polar vortex disruption, and it's exactly what happened around Christmas 2022, when Arctic cold pushed unusually far south, reaching all the way down to Florida. Europe sits well within range of the same effect whenever the polar night jet weakens. What actually weakens this jet stream? It isn't the Coriolis force that's driven by Earth's rotation and isn't going anywhere. It largely comes down to the temperature contrast at the edge of the vortex. Under normal conditions, the sharp clash between extremely cold air inside the vortex and warmer air pushing in from outside creates a strong pressure difference that reinforces the jet stream wall. But various factors, including how sea surface temperatures shift during events like El Niño and even solar activity, can disrupt that balance, sometimes weakening the polar night jet enough that it wanders off course, or in extreme cases collapses entirely for a period. This typically shows up as a rapid temperature spike high in the atmosphere over the pole, sometimes by as much as 50 degrees Celsius within just a few days, a phenomenon called sudden stratospheric warming. This kind of event isn't new or apocalyptic on its own. It happens periodically. The winter of 2009 to 2010 brought a genuinely record-breaking cold spell across parts of Europe, caused by exactly this kind of polar vortex disruption, with parts of Germany sitting under continuous snow cover for 59 days straight. There's real scientific reason to think these disruptions may become more frequent going forward, somewhat ironically, because rising Arctic temperatures could shrink the temperature gap between polar and mid-latitude regions, which is the very gradient that normally keeps the polar vortex stable and contained in the first place. There's an equivalent polar vortex over the southern hemisphere, too. And in 2024, researchers documented something there that had never been recorded before in the satellite era. Normally, the stratosphere above Antarctica sits around minus 80 degrees Celsius in winter. On July 7th, 2024, NASA scientists watched stratospheric temperatures there suddenly jump by 15 degrees Celsius, the earliest sudden stratospheric warming event ever recorded in that region's 44-year satellite dataset. Then, on August 5th, temperatures spiked again, this time by 17 degrees. Lawrence Coy and Paul Newman, atmospheric scientists at NASA's Goddard Space Flight Center, described being genuinely surprised by both events. Unlike the Arctic, which experiences sudden stratospheric warming roughly once a year, this kind of event happens over Antarctica only about once every 5 years on average, largely because the northern hemisphere has far more land-based terrain capable of disrupting airflow in ways that eventually propagate upward into the stratosphere. The Antarctic polar vortex, which normally maintains winds circling the South Pole at roughly 300 kilometers per hour in a fairly tight circular pattern, ended up stretched into an elongated, weakened shape, sometimes described as peanut-shaped, with noticeably reduced wind speeds. That had a real measurable downstream effect. It delayed the formation of the Antarctic ozone hole, which normally begins forming in early August. According to the Copernicus Atmosphere Monitoring Service, instead of the typical pattern of progressive deepening through the month, the ozone hole didn't really develop until later in August that year. A weaker, more disrupted polar vortex generally means less of the extreme cold needed to drive the chemical reactions that deplete stratospheric ozone. So, in this narrow sense, the disruption briefly worked in the ozone layer's favor. Scientists were careful to note, though, that a slow start to the ozone hole doesn't automatically mean the ozone layer is recovering faster overall, since its health depends on a genuinely complex mix of chemical and meteorological factors together. What actually triggered this unusual Antarctic disruption remains only partly understood. NASA researchers pointed to unusually warm conditions in the troposphere over Antarctica that July, the fifth warmest July on record for the region, with variations in sea surface temperature and SEA ice likely playing some role in disturbing the broader tropospheric weather patterns that then propagated upward into the stratosphere. Paul Newman has been candid that pinpointing exactly why these systems develop the way they do remains genuinely difficult. There's also a real, though not fully proven, suspicion that one earlier event contributed significantly to this anomaly: the eruption of the underwater volcano Hunga Tonga in the South Pacific back in 2022. That eruption sent an ash column an estimated 58 kilometers high, according to NASA, the highest eruption cloud D ever observed from space. And crucially, it injected an enormous quantity of water vapor into the stratosphere. Water vapor at that altitude can contribute to the formation of polar stratospheric clouds made of tiny ice particles, which create favorable conditions for the chemical reactions that accelerate ozone depletion. Researchers are still actively studying this connection. It remains an open question rather than a settled conclusion. Finally, the strangest story of all, Earth's own magnetic field, and specifically its magnetic North Pole, which has been behaving more unpredictably than at any point in modern measurement history. Worth clarifying first, the geographic North Pole is a fixed point where Earth's rotational axis meets the surface. The magnetic North Pole is different. It's the point where Earth's magnetic field lines dip straight down into the ground, and that point moves. It's been drifting steadily since its discovery in 1831 by explorer James Clark Ross. But over the past few decades, that drift has taken on a genuinely new pace. Since the 1990s, the magnetic pole's speed increased dramatically, from a leisurely 15 kilometers a year up to as much as 55 kilometers annually. Geophysicist William Brown of the British Geological Survey has described the pole's recent behavior as something researchers have simply never observed before. And then it got stranger still. After years of accelerating toward Siberia, the magnetic pole's movement suddenly slow, wet again in recent years, dropping from around 55 kilometers a year back down to roughly 40, which Brown has described as the largest deceleration ever recorded for it. First, a dramatic speed up, then a dramatic slowdown, all while still moving faster than the historical average. Why does this matter beyond compass accuracy? Earth's magnetic field is a massive protective shield against cosmic radiation and solar wind. Without it, life on Earth as we know it likely wouldn't be possible. The pole's movement gives scientists real clues about what's happening deeper inside the planet, since the magnetic field itself is generated roughly 2,900 kilometers down in the outer core, a massive sphere of molten iron and nickel in constant motion. That motion, combined with Earth's rotation, generates electric currents, and those currents generate the magnetic field, a process scientists call the geodynamo. The honest answer for why the pole is behaving this way right now is that scientists don't fully know. There are competing theories, changes in the flow of molten iron deep in the outer core, or shifts tied to the overall strength of the magnetic field itself. Geophysicist Ciaran Beggan of the British Geological Survey has explained that the field's total strength has been declining over the past few centuries, but unevenly, weakening over Canada while strengthening around Siberia, which is part of what's been pulling the magnetic pole in that direction. Over the past 200 years, Earth's magnetic field has lost roughly 9% of its overall strength. That might not sound dramatic on its own, but it genuinely concerns geophysicists as an ongoing trend. Some scientists have speculated this could be an early sign of a geomagnetic reversal, a process where Earth's magnetic north and south poles actually swap places. Before anyone panics, these reversals are a completely normal part of Earth's geological history, happening on average every few 100,000 years. The last major reversal happened roughly 780,000 years ago, meaning we're argua, Bly somewhat overdue by that historical average. Importantly, a reversal would not be some sudden single-day event. It would unfold gradually over thousands of years, giving humanity plenty of time to adapt. There's no strong reason to expect one within any of our lifetimes specifically. To keep pace with these ongoing changes, scientists regularly update something called the World Magnetic Model, which underpins navigation systems ranging from smartphones to military equipment. It's normally updated every 5 years, but in 2019, an emergency update became necessary because the magnetic pole was moving fast enough that the older model had become measurably inaccurate. Brown has explained that the longer you wait to update the model, the larger the resulting navigational error becomes. To put that in perspective, using an outdated version of the model to navigate a straight line roughly 8,500 kilometers from South Africa to the United Kingdom could leave you about 150 kilometers off target by the end of the journey. After all of this, it's worth addressing directly whether any of it connects to the earthquake and volcanic activity people always ask about whenever the magnetic field comes up. Based on the actual published science, there's no credible evidence linking Earth's magnetic field behavior to current earthquake or volcanic activity. Earthquakes result from tectonic stress building up in Earth's crust. The magnetic field is generated by circulation in the molten outer core. These are two entirely separate processes happening at completely different depths within the planet. The magnetic field also changes relatively slowly, while earthquakes and volcanic eruptions are sudden events triggered by geological stress reaching a breaking point. If the magnetic field were a meaningful driver of seismic activity, we'd expect to see a measurable correlation between magnetic fluctuations and earthquake activity. In the data, no study has ever demonstrated that connection. Throughout history, major earthquakes and volcanic eruptions have occurred regardless of what the magnetic field happened to be doing at the time. The ground shakes because of ordinary tectonic forces, not because of a wandering magnetic pole. Taken together, these four systems, ocean circulation, the jet stream, the polar vortex, and Earth's magnetic field, really do show genuine, well-documented, unusual behavior happening at roughly the same time. But unusual and worth studying closely is a meaningfully different claim than connected by one single underlying cause. The honest scientific answer right now is that these are largely separate systems, each responding to its own specific mix of natural cycles, and in some cases, genuine climate change influence, rather than one unified signal pointing toward a single dramatic event. AMOC responds mainly to freshwater input from melting ice. And long-term thermohaline dynamics. The jet stream's recent instability is best explained by El Niño with climate change, as an amplifier riding on top of it. The Antarctic polar vortex disruption traces back to an unusually warm troposphere and possibly lingering effects from a volcanic eruption 2 years earlier. And the magnetic pole's erratic sprint and sudden deceleration trace back to fluid dynamics in the outer core, thousands of kilometers beneath our feet, that has nothing to do with the atmosphere or the ocean at all. And that's actually the more fascinating takeaway. Not that Earth is sending one coordinated warning, but that several genuinely independent, enormously complex systems are all quietly reminding us how much we still don't fully understand about the planet we live on. The real story here isn't a single ticking clock. It's a planet with more moving parts than any one headline can capture, each one worth watching closely, and none of them worth panicking over on their own.